Hey guys, this is section 9.10, the ideal dilute solution. So for real solutions, we don't have a simple mathematical model, but real solutions do have a limiting behavior. And that is, as they become more and more dilute, they behave like ideal solutions. So we're going to look at that limit here. Starting with a real solution at equilibrium, we know, just as for an ideal solution, that the chemical potential of component I is equal to the chemical potential of pure component I plus RT ln vapor pressure of component I over the vapor pressure of pure component I. Now, for pure substance, the chemical potential of the vapor is equal to the chemical potential of the liquid. We'll just call that the chemical potential. But for a real solution, not an ideal solution, the vapor pressure of a component is not equal to the mole fraction of that component times the vapor pressure of the pure component. That's because, think A-B, right? The A-B interactions are not equal to the AA and BB interactions. They're different. So for when we have for a solvent in a dilute binary solution, we define something called its activity, A. The activity of the solvent as being equal to the actual pressure of that solvent above the solution divided by the vapor pressure of that pure solvent. And that's the activity. Now, if it's an ideal solution, then the activity of the solvent is equal to the mole fraction of the solvent, and we get Reynolds Law. We define also something called the activity coefficient. This is supposed to be a gamma for a real solution. The activity coefficient of the solvent is equal to the activity of the solvent over the mole fraction of that solvent. So in the limit, as this becomes an ideal solution, the activity is equal to the mole fraction, and the activity coefficient becomes 1. And it also helps to look at this as the activity is equal to the mole fraction of the solvent times the activity coefficient of the solvent. This activity coefficient, the gamma, guys, it's a measure of how non-ideal a solution is. It's like the fugacity when we talked about the fugacity of a gas. Activity coefficient is to a real solution like fugacity is to a real gas. And again, as the solution becomes more and more dilute, the mole fraction of the solvent goes to 0, the activity coefficient goes to 1. Now we know that the chemical potential of component I is equal to the chemical potential of pure component I, right here, plus RT ln of Pi over Pi star. For a real solution, okay, we can replace this by the definition of the activity, and we get this equation right here. This is the start of the rest of the chapter, basically. We're going to use this for the rest of the chapter. Now, because we look at different limits if we're talking about the solute or the solvent, okay, defining an ideal solution. So an ideal solution is one as the mole fraction of the solute approaches 0, which means the mole fraction of the solvent approaches 1. That means we have different expressions when we're looking at the partial pressure of the gas due to one of the components above the solution versus the mole fraction of that component. This graph right here, this is for a carbon disulfide acetone solution. This red line here is the actual vapor pressure of the acetone above the solution. The dashed line is Reynolds Law. We'll get to Henry's Law in just a moment. Well, we can see a couple things. As the x-axis is the mole fraction of the carbon disulfide. So anything less than here, halfway, the carbon disulfide is the solute, acetone is the solvent. And as this becomes more and more dilute, go to the left down here, the mole fraction of the solute, the carbon disulfide, goes to 0. Then the solution starts to obey Reynolds Law, get to Henry's. Reynolds Law up here, it starts to become linear right up in this region right here. Now, if we were to look at the vapor pressure of the carbon disulfide instead of the vapor pressure of the acetone, we would see the same sort of behavior as the, if we were plotting the mole fraction of the carbon disulfide down here, then as we go to this end right here, it would obey Reynolds Law closer and closer. Now, we can see from this graph that down here, when the carbon disulfide is the solvent, that the vapor pressure of the solute, the acetone, its behavior looks linear down here, but it's not Reynolds Law. It's a different slope. It's called Henry's Law. It ends up that the vapor pressure of the solute is equal to the mole fraction of that solute times a constant called Henry's Law constant for that solute. KH is Henry's Law constant. And it obeys this equation as the mole fraction of the solute goes to 0. So in this equation right here, this is a mole fraction of carbon disulfide. To this side of halfway, carbon disulfide becomes a solvent, and the acetone becomes the solute. So as the mole fraction of the solute goes to 0, the mole fraction of the solvent goes to 1, the vapor pressure of the solute starts to obey Henry's Law. So this is an important one, Henry's Law right here. Henry's Law constant gives us some information too. So as a solution approaches ideality, so it becomes more and more dilute, the value of Henry's Law constant for a component approaches the vapor pressure of the pure component. And the size, the magnitude of Henry's Law constant, it gives us a measure of deviation from ideality. Sometimes Henry's Law's constant is less than the vapor pressure of the pure component, and sometimes it's more. If it's less than the vapor pressure of the pure component, that tells us there's a negative deviation from Reynolds Law. Remember, that's where the A-B interactions are stronger than AA and BB. And Henry's Law constant is greater than the vapor pressure of a pure substance for a positive deviation from Reynolds Law. Remember, that's the A-B interactions are weaker than the AA and the BB. So here, finally, we have a really good definition of an ideal solution. It's defined as a solution whose solvent obeys Reynolds Law and whose solute obeys Henry's Law.